Section 5.9, repeated eigenvalues. Ready to consider the third possibility when it comes to the different types of eigenvalues. In 5.7, we looked at real distinct eigenvalues. In 5.8, we looked at complex conjugate eigenvalues. So this is our third case where we have a real valued eigenvalue, but it's repeated. So it has a multiplicity of 2 or higher. So far, the previous two sections have sort of demonstrated that our methodology from chapter 3 works pretty well. So what we'll do in this lecture is start by trying to emulate the methodology that we used to deal with a repeated root back in chapter 3. And as it turns out, spoiler alert, that's not going to quite work. So there is an extra complication that we need to address, and that will become clear as we try to derive a general solution. So let's take a look at how this plays out. So first, in this paragraph here, I just lay out the ingredients that we'll be working with. We're going to assume that A is a 2 by 2 matrix, and we can eventually generalize this to larger coefficient matrices, but for our purposes in this derivation, we're just going to start with this kind of smallest interesting case, a 2 by 2 matrix. Next, we'll assume that A has one real eigenvalue, lambda, one and only one. So my characteristic polynomial is such that there's a linear factor that's squared, and so the eigenvalue that comes out of that characteristic polynomial is just by itself, there's just one. And then we assume that we can find the associated eigenvector, which we'll continue to call eta. First things first, I will build a solution by taking eta e to the lambda t, and I am confident that that is a solution. I've included an unknown constant here, and then I've called this x sub 1, like x vector sub 1. That's just to indicate that this is one of the solutions of my system, and that's not to confuse this x1 with like a component in a vector, which doesn't have the vector hat on it. So based on chapter 3, we know a couple things. First of all, we know that we need a second solution. I can't just write this as my entire general solution. I need a second solution, call it an x sub 2. Moreover, whatever that second solution is, it has to be linearly independent from this first solution. So I've laid out two strategies that we could use to try to address this. Our first strategy hinges on the fact that any constant multiple of an eigenvector is also an eigenvector. So if I look at this solution here, x sub 1, that I've built using eta, I could, in theory, just multiply eta by a constant, say 2. 2 eta would be itself an eigenvector. Therefore, 2 eta e to the lambda t would be another solution to my differential equation, or my system. That is true, but such a solution wouldn't satisfy this second requirement. Constant multiple of eta in this solution would not yield a linearly independent solution. So I can't simply multiply this by some constant. Even though that would give me a solution, it's not going to work to build my general solution because it would not be linearly independent. The second approach that I've labeled number 2 here is more similar to what we tried in chapter 3. Let's try to address this linear independence issue by multiplying our known solution not by a constant, but by t. Taking that approach, our second solution would have this form here. I've left off, for the purpose of the derivation, I've left off the constant. And as I mentioned, we could maybe call this x sub 2. So then my general solution will be the x sub 1 from above plus c sub 2 times this x sub 2. But for the purposes of this derivation, it's just a little cleaner to work without that constant. So let's take this form of a solution and let's plug it into our differential equation. I need x prime, so I need to differentiate this. Remember that this eta vector is constant, and so I can treat it as I would treat a normal constant, and when differentiating, I just have to deal with this t e to the lambda t product. So down here, where I've plugged in that x vector, on the left, where I have x prime, you'll see I essentially have the product rule, and I've treated this eta vector as constant. Applying that product rule, I take the derivative of t and multiply by e to the lambda t. Here I've taken the derivative of e to the lambda t, which gives me lambda e to the lambda t. So this is the derivative on the left. This is x prime. And on the right, I just have a times x. Now, we have two different types of terms in this equation. I have these two terms here, which have the form t times e to the lambda t. And then I have this term here, which is just an e to the lambda t. If I wanted to, I could sort of imagine that I've got that same term on the right-hand side. It's just that its coefficient is 0. So what I need to do to try to understand how to solve this equation is to set like coefficients equal. So let me take a look at the coefficients on, say, just the exponential terms. And setting the coefficients from those terms equal, I get eta on the left-hand side is equal to the 0 vector on the right-hand side. Playing the same game with these e to the lambda t terms, I get lambda times the vector eta on the left, and then a times the vector eta on the right. Again, remember I'm just grabbing the coefficient, so I won't have this e to the lambda t term involved in this equation. This second equation implies, if I just rewrite it by switching signs, I get a times the vector eta equals the vector eta multiplied by a constant. So this is the eigenequation, and this implies that eta needs to be an eigenvector of my matrix A, and lambda has to be the corresponding eigenvalue. That feels totally natural. That feels exactly like what I would do to normally identify what eta and lambda would need to be in order for this function to be a solution. So that part I'm comfortable with. On the top of the next page, I point out that this first equation says that in addition to this being true, it must also be true that eta must equal the 0 vector. Unfortunately, when we started defining eigenvectors, we prohibited 0 from being an eigenvector. So this second equation tells me that eta must be an eigenvector. This first equation tells me that eta must equal 0, and those two equations contradict each other. So that implies that this solution that I started with, that I was postulating here as a potential solution, is not going to work because it has led to two equations which contradict each other. So how do we fix this issue? As I've noted in the second paragraph here, the issue seems to be that x prime has an e to the lambda t and a t e to the lambda t, but x, the original postulated solution, only has a t e to the lambda t. So what if we were to add an e to the lambda t term to our postulated solution x? Here's what I've done. I'm going to suppose that my solution x not only has a t e to the lambda t and with a coefficient vector eta, but I'm going to add an additional term which has some new coefficient vector rho times e to the lambda t. Back in chapter 3, this would not be okay because this e to the lambda t would be repetition with the previous solution, but in this particular case, let's see if this is necessary. Once again, taken my original system, x prime equals ax, and I've plugged in this function along with its derivative. If we think about the derivative of this first piece will be exactly the same as the derivative we saw previously. I apply the product rule and I get these two terms here. How about the derivative of rho e to the lambda t? Well, rho is simply a coefficient, so the derivative of e to the lambda t will be lambda e to the lambda t, and that coefficient rho is just kind of along for the ride. Now, on the right-hand side, I have a times the vector x, so I have to grab this entire vector here and put that in. I want to set like coefficients equal again. Before I do that, just to clean up this right-hand side a little bit, let me distribute the matrix A through to each of these vector function expressions. And now I once again notice that I've got t e to the t terms on both sides, and I also have e to the lambda t terms on both sides. Here I've color-coded those two different types of terms, and I don't know if you've noticed that I've recently figured out how to do this little shading thing, and I really like that trick. So I've been using that a lot. Using that trick, I've color-coded my t e to the lambda t terms in pink here, and then my regular just e to the lambda t terms in orangish, peach-ish. So let me go ahead and set like coefficients equal. This second equation, which contains the coefficients on t e to the lambda t, once again yields my eigenequation, and so that once again tells me that eta has to be an eigenvector of A, which corresponds to the eigenvalue lambda. Nothing different there. How about here, if I look at the coefficients on the e to the lambda t terms, this now says that eta plus lambda rho needs to equal A times rho. Previously, this first equation led to a contradiction with the second equation. So the question is now, is it possible for both of these equations to be consistent? Again, the second equation indicates that eta needs to be an eigenvector. What does this first equation tell me about eta and rho? I've rewritten the equations here. A times the vector rho equals lambda times the vector rho plus eta. This first portion, A times rho equals lambda times rho, almost feels like the eigenequation. Feels, as I've put it here, sort of like I have the eigenequation and then I've just tacked on rho. So it's not exactly the eigenequation, but if I move the vector rho to the left and then do some slight rearranging, I get this equation here. Now this equation, if eta was 0, this would be the eigenequation, but it's not. But eta is an eigenvector. This equation is known as the generalized eigenequation. And it basically says we first need to solve for an eigenvector, an actual eigenvector of the matrix. That's what this eta is. And then we can set up this equation and solve this equation for rho. When we do, rho is called a generalized eigenvector of the matrix A. There is no reason that these two equations are inconsistent or somehow contradict each other, and it will in fact be possible to first solve this equation, the regular eigenequation, to get eta, and then use this generalized eigenequation to get this second necessary ingredient, this vector rho. So that indicates that this solution works, meaning that it is in fact a solution. Is this solution sufficient to build a general solution to my system? I haven't worked through the details here, but I do point out that it can be shown that this function is in fact linearly independent from our initial function. So I can use these two ingredients with a necessary coefficient added on to this second part here. I can use those two to build a general solution to our system. So this solution here is the key to address the issue that we saw earlier, and the linear combination of these two will be my general solution. I've summarized that fact in Theorem 1 here. So Theorem 1 states that if my matrix is 2 by 2 and I have one single repeated eigenvalue and the corresponding eigenvector is eta, then in order to state the general solution of this system of differential equations, I'll build it out of the two solutions that I just highlighted. The first one will be the natural solution that we would normally build, and then the second one will include this t e to the lambda t term with eta as a coefficient. And then in addition, I also need to include another e to the lambda t term, but I'll have a different coefficient function on that term there. So this is the quote-unquote formula that I will use to build solutions in the case that I have a repeated eigenvalue. And then just as a reminder, I've stated the generalized eigenequation here to indicate how I will solve or compute that vector rho. Let's go ahead and try out some examples. This first example is kind of awesome in a sad, comical way. So in our last lecture, in the first example, I had a typo, and in the last lecture, I needed the matrix to have complex eigenvalues. If I had used the original matrix, this original matrix has a repeated eigenvalue. So what I thought I would do in this lecture is use the matrix that has a repeated eigenvalue, but I accidentally copied and pasted the one that has complex eigenvalues. So I once again have a typo in my very first example, and I intended that to be a -1. I am hoping that I have significantly fewer typos in this lecture than I did in the previous lecture. In fact, I'm really hoping that that's the only mistake I've made. Got my fingers crossed. So using this matrix 3, -1, 4, -1, let's go ahead and try to solve the system. I will start as usual by finding the eigenvalues and eigenvectors, but as suggested by the section that we're in, I expect that I'll get a repeated eigenvalue. Let's see if that's how this plays out. Looking through these steps here, I use the typical equation to solve for lambda, and my characteristic polynomial became lambda squared minus 2 lambda plus 1, which can be factored as lambda minus 1 squared, which yields a single real eigenvalue, lambda equals 1, and I just write repeated here to reinforce the fact that it has multiplicity 2. In the usual way, I find the corresponding eigenvector, and so I've got the sort of traditional components to my solution. I know that I'll have c sub 1 e to the t with this coefficient vector as the first component of my general solution. Now, in order to find this second component, I need to calculate rho. And I'll remind you the equation that rho satisfies is this equation here, a minus lambda I times rho equals eta. Notice that I now know what lambda is, it's 1. In fact, the matrix A minus lambda I is exactly this coefficient matrix that I just utilized a second ago to solve for eta. In this previous calculation, the right-hand side, the augmented vector, was the 0 vector because I was solving the equation A minus lambda I, eta equals 0. Now I'll have that same system, but on the right-hand side, I'll have this vector, eta. Let me show you what I mean. Written as an augmented matrix, I have this system here where the coefficient matrix is A minus lambda I. I'm using lambda equals 1. And then the right-hand side, the augmented vector, is not 0 in this case, but instead it's eta, the eigenvector that I just found. Simplifying that system and then using one of the equations to get a relationship between the two components of the vector rho, I think I get that rho sub 2 has to be 2 times rho sub 1 minus 1. Plugging those in to an actual vector, this again says that I can choose any value I want for rho 1, and then rho 2, the second component. It sounds like I'm saying the second row of the vector, but I'm actually saying rho 2, like the variable rho sub 2. Anyways, that will be 2 times whatever this choice is minus 1. Now, typically when I'm building an eigenvector, I make a convenient choice for this free variable. I have to approach things in a slightly different way this time. What I'm going to do next is I'm actually going to break up this vector into the row part and the non-row part. Here's what I mean. So I've decomposed my vector rho into this part, which involves the free variable rho sub 1, and then this part, which is just sort of constant and unaffected by that free variable. If you look at this coefficient vector that we're multiplying by rho sub 1, that's exactly eta. And that is not a coincidence. That should always happen when calculating a generalized eigenvector. So since, in a certain sense, that vector is already represented in our solution, that is to say, this vector 1, 2 and the eta vector are linearly dependent. They're in fact equivalent. I want to exclude that portion from my actual generalized eigenvector rho. So this is kind of a strange step, but I'm going to actually choose rho sub 1 to be 0. And I'm going to select just this second constant component to be rho. I can in fact choose a different value for rho sub 1 here, or whatever the free variable happens to be, but this is the customary choice, to just isolate this constant part as the generalized eigenvector rho. So now that I've got all of those ingredients, I can write my general solution. Not surprisingly, I don't have any room to write my general solution. I'm going to go ahead and write it sort of up here above my original problem. So putting all these ingredients together, I get this general solution where the first component feels to me just kind of natural and pretty straightforward. I have e to the lambda t, and then as the coefficient on that exponential function, I have the associated eigenvector. And now this second part is a little bit different. It feels a little bit out of the ordinary here. I do have my e to the t term with the associated eigenvector. In addition, I have another e to the t term with, as its coefficient, this generalized eigenvector. So that's the part that's really distinct. So that's the process that we use to solve a system when we have a repeated eigenvalue. We've got just a couple more examples that kind of explore this method in a little bit more detail. In example 2, we have a 3x3 system, and we have been provided with an initial condition. Therefore, we'll have initial value problem to solve. One thing as I notice as I'm getting prepared to sort of do my standard calculations here is that this matrix is triangular, and again the definition there is that if you look at the diagonal entries of a square matrix, if there are zeros above that diagonal or below that diagonal, in this case we have only all of my entries above the diagonal are 0. And so if we can identify that that is true of our matrix, then we can conclude that the eigenvalues are directly these diagonal entries of the matrix. This is a result of the nature of the determinant calculation. If we were to put minus lambdas along the diagonal and then do the full determinant calculation, it would just work out that our eigenvalues are these diagonal entries. In the name of efficiency, I'm going to go ahead and just use this property and state that my eigenvalues are the numbers 1 and 2, and I emphasize here that the eigenvalue 1 occurs twice. So that's a repeated eigenvalue. So I will have to utilize the methodology that I just demonstrated in the previous example to not only find an eigenvector associated with 1, but also a generalized eigenvector, and then the solutions, plural, the two solutions that derive from this eigenvalue will have the structure that we stated in theorem 1. Lambda equals 2 is not repeated. It's a distinct eigenvalue, so I can just use the sort of quote-unquote traditional technique to build a solution using that eigenvalue once I've found the associated eigenvector. In fact, let's start there. Let's start with lambda equals 2 because this one is a little less involved. Let's find the eigenvector associated with lambda equals 2. Here I've followed the usual steps and I've found the eigenvector associated with lambda equals 2. Now I will use the process that I demonstrated in the previous example to find the actual eigenvector associated with lambda equals 1 along with the generalized eigenvector that's associated with lambda equals 1 as well. So here I've solved for the actual eigenvector associated with lambda equals 1. Now I will solve for the generalized eigenvector rho using this equation here. Notice I've already plugged in the specific alpha value of 1. And then rho is what I'm going to try to solve for. And on the right hand side, instead of having 0 there, as is customary in the regular eigenequation, I have instead this vector eta that I just calculated, specifically here, an eigenvector. So I believe my generalized eigenvector rho will be given here as I've highlighted it in green, -1/4, 0, -21/4. And let me just remind you of a couple steps of this process. Of course, we begin with the coefficient matrix A minus lambda I. Lambda is equal to 1. So if I look back at my original matrix A, here I've just subtracted 1 along the diagonal. And then I augment that with the eigenvector that I found in the previous step. Follow the usual linear algebra matrix operation steps. And then that eventually gives me an equation here, or an expression here for rho, like rho 1, the first component has to equal -1/4. This second equation, of course, tells me, as I've written here, 6 times rho 2 plus rho 3 equals -21/4. And then the key step is to take this version of your generalized eigenvector rho and split it into these two components. The portion that contains the free variable, which in this case is rho 2, along with this constant portion. It is, again, no coincidence that this portion, which is multiplied by the free variable, this vector, is exactly the same as the eigenvector eta that we found previously. And since that is in a sense already accounted for in our solution, I will choose row 2. I'll choose this free variable to be 0. Therefore, my final generalized eigenvector will be just this constant portion here, as I've highlighted. All right, once I've worked through all of those steps, I think I'm ready to build my general solution. And I'll once again remind you that we have two different types of eigenvector, eigenvalue. So we'll have two different sort of types of solutions. And I just need to use all of the necessary ingredients to build that general solution appropriately. So here's that general solution, and last step will be to incorporate initial conditions. And here are the steps that will enable me to solve for my coefficients C1, C2, C3. If I've done everything correctly here, then it looks like C1 will be 39, C2 will be 2, and C3 will be 4. Let me go ahead and plug those into my general solution. So this is, of course, my final solution and acceptable version of it. Once again, I've got lots of like terms and lots of zeros actually in these coefficient vectors. So I don't think it'd be too hard to actually write out the individual functions that are represented here. So let me go ahead and take a second to do that. So if I have broken these up correctly, I think these are the three solution functions that I get. And as I predicted, x1 is quite simple. x2 is as well. And x3 is a little bit more complicated here, but I just think it's helpful, as I've mentioned before, to rewrite the solutions in this form, just kind of as a reminder that we're dealing with regular functions. I just have x1 equals e to the negative e to the t. And the nature of these functions is sometimes masked by this vector representation or this vector notation. This final example, example 3, is sort of a summary of the three different cases that we've considered so far, and it asks us to identify values for these matrix entries, A, B, C, and D, which will force all of the solutions of the system to tend to 0, that is, have a limiting value of 0. This is similar to problems that we've seen previously, particularly in chapter 3, and basically it's asking what has to be true about this coefficient matrix in order for all of my solutions to go to 0, and I'll need to consider the three different possible cases for eigenvalues that could potentially result from this coefficient matrix. So let's, of course, start there. Let's calculate the eigenvalues of this matrix. So I've started that calculation here, and not surprisingly, my characteristic polynomial is kind of complicated because I'm dealing with these arbitrary values and I can't simplify anything. So I get this equation here as my characteristic equation. And then since this is a quadratic and I don't know exactly what these coefficients are, my only strategy, my only tool here is to use the quadratic formula. So I've written out the quadratic formula here, and then there's some simplification that I want to do underneath the square root. I just cleaned up this quadratic a little bit. I could factor a negative out. So this is actually a plus d squared. And then this is clearly minus 4 times ad minus bc over 2. Now, typically, I would try to analyze this discriminant in order to identify when, that is, for which values of a, b, c, and d, the three cases would occur regarding the different types of eigenvalues. Instead of taking that approach this time, I just kind of want to think about the role that the different components of these eigenvalues play in the general solutions that we've seen in each of these three cases. So let me explain what I mean in terms of like this first case. The first case we typically think of is that I'll have real distinct eigenvalues. And if that is true, then my general solution will have this form here. Now, in this statement of the problem, we want solutions to approach 0. So the way that that will happen is if both lambda 1 and lambda 2 are negative. So looking at the structure of the quadratic formula, or the structure of these eigenvalues, it's described here by this quadratic formula, we know initially that that is likely to occur when this a plus d term is negative. If this a plus d term is negative, then, well, we're guaranteed that one of the two eigenvalues will be negative because I'll have a plus d, which again we want to assume will be negative, minus this square root quantity, and this square root quantity will be positive. So the first restriction that I want to implement is that I need a plus d to be negative. Now, if a plus d is negative, there's a chance that when I add this square root quantity will be larger than a plus d. And so the overall eigenvalue would end up being positive. That would, again, be the case if this was a negative, but when I add this square root, it's something positive. I know for sure it's positive. And if it's larger than this quantity, then my overall eigenvalue is positive. So I'm going to make an additional restriction that when I do add in this numerator, that overall quantity ends up being negative. I can actually simplify this requirement a little bit. For example, let me move one of these over to the other side. I guess I'll move this a plus d over. Now I can square both sides. Squaring the right-hand side, squaring this negative will make this positive. And of course, squaring the left-hand side will just cancel out the square root. Next, it's clear that I could cancel these a plus d square terms on both sides. That'll leave negative 4 times this quantity is less than 0. When I divide through by the negative 4, that will of course change the direction of the sign. So I think finally I'll have that the quantity AD minus BC must be greater than 0. I could move the BC over, but you'll probably recognize this as the determinant of my original coefficient matrix. And so there's two requirements that must be in place here. First of all, A plus D has to be negative, but then secondly, the determinant of the matrix, AD minus BC, has to be positive. So what I've determined here is that if this eigenvalue expression yields real distinct eigenvalues, then what needs to be true is that both these two criteria here are met. Let's perform that same sort of analysis in the second case where we have, I guess we could consider either of the two. Let's look at the case where we have a real repeated eigenvalue. And as we've seen in this section, the general solution for the case when I have a real repeated eigenvalue will look like this. And all of the function terms in this general solution are all just e to the lambda t. We do have a t e to the lambda t, but as t grows large, this exponential will dominate over this linear term. And so really all of the dominant terms in this function are just these exponentials. Therefore, in order to force those to approach 0 as t grows without bound, lambda needs to be negative. In this repeated eigenvalue case, the square root part of the quadratic formula goes to 0, and so I can explicitly state what lambda will be. Namely, lambda will simply be a plus d over 2. Therefore, if I need lambda to be negative, then once again, I simply need a plus d to be less than 0. That leaves the third case where I have complex conjugate eigenvalues. And in that case, we know that our general solution has this form here. We know, let's look at some components here. We know mu is going to affect the rate at which these trig functions oscillate, but the overall behavior of these solutions will always be driven by this exponential. And the coefficient C1, C2, the coefficient vectors A and B will similarly not have a qualitative effect. Really, the only thing that's driving the overall qualitative behavior of these solutions is these exponentials. And once again, we need those exponentials to go to 0. The notation here is a little different. If you remember, lambda here is just the real part of the complex eigenvalues. But looking back at the structure of the quadratic formula, we can see that that real part will once again be simply a plus d over 2. Therefore, in order for, in this case, to ensure that solutions will approach 0, we once again need a plus d to be less than 0. So looking back over these three cases, we're starting to see a trend here. In all three cases, it needs to be true that a plus d will be less than 0. And then in this first case, it needs to additionally be true that this determinant AD minus BC is positive. So as long as I satisfy both of those conditions, then I'm guaranteed that the solutions will approach 0 as t grows without bound, no matter what the constants, c1, c2, no matter what the coefficient vectors happen to be, I'm guaranteed that the solutions will go to 0. All right, that wraps up section 5.9.